خلينا نتذكر شوي ال current characteristics للموسفيت. So if you recall, the MOSFET has a gate. خلينا نغير الكولر بس. It has a gate, drain, and its source. Source هو على طول محل ما نحن we have the arrow. Okay, and this one where the arrow is going outside to the outside of the transistor, this one is an NMOS device. يعني هي عندها NMOS channel, N-type channel. Okay, and in this case, since we are only interested in the amplification mode, يعني لما تكون الديفايس عم تشتغل بالهاي جين region، الموسفيت عادة حيكون بالsaturation، والsaturation conditions هن إنه يكون أول شيء الترانزستور on، يعني VGS أكبر من VT. وللموسفيت عادة هيدا الرينج الVT في يكون 0.2 في يكون 0.7 هالأيام 0.5. Earlier it used to be 0.7. And the other condition is the saturation condition itself. And this saturation condition itself عنا فيها بيكون إنه ال VDS اللي هو من هون لهون بين drain والsource is greater than VGS minus VT اللي هي كمان نحن كنا نسميها VOV أو الأوفر درايف. يعني لما ال VDS تكون كبيرة بيكون الترانزستور بال saturation mode. هلا هيدي للأنموس. إذا مذكرين للبيموس كنا ناخد يا إما VSD، كنا ناخد VSD، كنا ناخد VSG صح؟ وكنا ناخد absolute value of VT، إذا في لمدا absolute value of lambda، ونخلي ال conditions هن ذاته. أوكي؟ هلا you can take the absolute value of VDS and you can take the absolute value of VGS and absolute value of VTP، بس the latter is easier لأنه إذا عم نحل ماننا مضطرين نفكر in what direction the absolute works. أوكي؟ مثل ما في عنا saturation بالموسفيت ليشتغل بالamplification mode، we have in the BJT, okay, it is the bipolar junction transistor. ال BJT بيفرق عن الموسفيت. هيدي الموسفيت عنده الاي هون بالجيت هي 0 وعنده quadratic equations نطلع عليها بعدين. ال BJT عنده لا 3 currents are there, IC, IB and IE. Okay, and the MOSFET has to be for amplification in the active mode. Okay, بده يكون بالactive mode. وبالactive mode يعني الديفايس بدها تكون on. بدها تكون on. هيدا هو NPN ترانزستور، يعني هاي NPN. اوكي، بدها تكون هيدي الجنكشن من ال P لل N on أكبر من 0.7، VBE أكبر من VBE on. هيدا إذا مذكرين هو البيس، هيدي النود هي الكولكتور، وهيدي النود هي الإميتر حد الأرو لل NPN transistor. Okay, so in this case هيدي اتفقنا الكولكتور node. This is the collector node, base node, emitter node. Okay, and this is an NPN. مثل ما عندي NPN كمان في يكون عندنا PNP الترانزستور هلا بنحكي عليها آخر شيء. طيب ليكون بالactive mode اللي هو بيعمل لي amplification. Okay, what this does is I have to have it on، يعني forward biased هيدي، و I need also to have VCE large. هيدي VCE من هون لهون مثل parallel للشيب للموسفيت. ال VCE بدها تكون كبيرة، كون أنا بالactive mode أكبر هون من constant، أكبر من 0.3 volts. Okay, so this is the basic operating region that we care about for the MOSFET devices and the BJT devices. طيب hold two regions, let us clear this, and in those two regions I have to know how to utilize the currents. هيك لنتذكر ليش أنا بدي أعرف الكرنت، لأنه إذا مذكرين نحن كنا نعمل أول شيء إذا بدي أدرس الجين ال DC operating point من الدي سي operating point طلع اي دي مثلا بالموسفت و في او في. من هيدي الكوانتيتي كنت طلع البارامترز لسمول سيجنال موديل اللي هن جي ام و ار او، ومن هيدي كنا نرسم السمول سيجنال سيركت اناليسيس ونطلع الجين. هلا رح نمرق فيهم بس حبيت اعمل لكم ريفرشر انه هو هن 3 steps that we care about. طيب فاذا انا لازم اعرف ال current characteristics لهوت transistors بهالريجن اللي هي saturation بالموسفت. And in this case for my MOSFET هو عنده هيدا ال current لإله. This is IG here and IG is 0 and this is ID and IDS بينزل بالدرين برانش وبكفي على السورس برانش، يعني نفس الكارنت اللي جاي هون هو ذاته نازل مكفي. وهيدا الدرين كارنت هو half mu n C ox W by L VGS minus VT square. You know this equation more by half K prime W by L ضرب VOV square where VOV is the VGS minus VT. Okay, so إذا عنا channel length modulation كنا نضربها للإيكويشن ب 1 plus VDS على VA where VA is a given early voltage. إذا مذكرين كنا نحكي إنه ال current characteristics لل device هي إذا هيدي هي ID وهيدي هي VDS. أوكي، كنا نقول for a given voltage VGS my current will keep increasing until VDS increases ليصير قد ال VGS minus VT. ساعتها بفوت بال saturation region. Okay, وكنا نقول إنه the saturation current is roughly constant. However, if there are some secondary effects اللي هن ال early effects بصير الكارنت هيك بسيط عنده شوي slope صغير. هيدا slope بنعمل له modeling with this equation a small increase with VDS and عنده slope 1 على RO. slope بيساوي 1 على RO اللي هي الاوتبوت intrinsic output resistance للترانزستور. فإذا حدا عنده سؤال عن saturation current equation للموسفيت؟ Okay. طيب so فإذا therefore in the saturation region which is when VDS is greater than the specific VGS minus VT that I am operating at, we will have the transistor operate with this current equation, and if we have an early effect we will add this component to the equation. Okay. طيب great. هلا هون عم بكفولنا انه شو هن هول البارامتر. هلا one little thing that I need to add انه إذا كانت هيدي مثلا VGS هي 1 فولت لنقول إذا أنا عليت له ال VGS عملتها 1.5 فولت it's going to follow another graph على ال 1.5 فولت وبتصير بتعمل saturation على value تاني اللي هو 1.5 minus VT. فإذا نحن إذا عرفنا ال VGS بنعرف على أي كيرف الأزرق أو الأخضر الكرنت ماشي، لأنه هي بتغير لي هيدا الفاليو هون. وهيدي الإيكويشن هي بس للساتوريشن ريج. أوكي؟ طب معنا نطلع باللي قبلها باللينير ريج. طب so if we come here and look at the rest of the slide عم بخبرني إنه ال K prime N هي mu N C ox، وعم بخبرني إنه البارامتر VA اللي هو ال early voltage هو VA prime ضرب L. يعني إذا عطوني constant VA prime حسب اللينكس للديفايس فيني طلعه لهيدا ال VA. So it's another given that I need to recall. And now let me clear this. طيب هلا عم بقول لي للبي جي تي مثل ما الموسفيت بده يكون بالسات البي جي تي بده يكون بالاكتف، وعنده set of equations هيدول الايكويشنز. أول شي نحن بنعرف إنه IB هو IC على بتا، صح؟ بالبي جي تي. وبنعرف إنه ال IE هي IC plus IB، يعني هي بتا بلس 1 ضرب IB. أوكي، أو فينا هيدي نقولها إنه IC هي بتا IB. أوكي، بتا ضرب IB. طيب أعطاني قال لي خلص you can use this equation IC هي IS e to the VBE على VT. Okay, and then you can derive IB from this equation here by dividing it by beta. Okay, in case there is an early effect تدخل نفس الشيء equation لل 1 على VCE 1 plus VCE over VA على multiplication factor as a multiplication factor ضرب ال IC equation. يعني بصير كمان هو عنده شوية هيك slope، وهالslope will correspond to some intrinsic resistance in the circuit. طيب هيدول هن DC operating point elements or characteristics. So these are the DC components. هيدول هن DC. And now we need to look at the AC. يعني بدنا نعمل small signal analysis. So to study the small signal analysis نحن حكينا عن شيء اسمه الباي model. Okay, so خلينا نحكي عن الباي model. So we have the hybrid pi model, and in the hybrid pi model رسمناه لنقدر ندرس small signal analysis لل circuit. What we see here on the left is really the pi model for the MOSFET, and here we see that هيدي الجيت، هيدي الدرين، وهيدي السورس. ونحن عنا whatever VGS is in the small signal circuit, there will be a current that will flow from the drain to source. value تاعونه بيساوي GM VGS. Okay, هلا this is the pi model for the MOSFET, and okay, and we use it for small signal analysis. And then corresponding to it, so فوق هيدول قلنا هن DC. okay, corresponding to it في عندي هلا إذا كان عندي effect لل early voltage، يعني أنا إذا كان في عندي slope هون حينزيد عندي resistor RO هون بالequivalent model. Okay, many times in the analysis we tell you ignore RO and DC، يعني احسبوا ال current equation بدون هاليلو، بس consider it in the small signal analysis. هيك حتشوفوا إنه مش بهالlecture بس ب other lectures we will start to tell you that. So keep this in mind. للبي جي تي لأنه عنده IB وال IB exists and it's different from zero. Okay, so حيكون في عندي resistor هون اللي هو R pi. Okay, and we will also have the same RO effect كمان موجود هون ال RO إذا عندي هيدا الترم موجود هون. فإذا بالبي جي تي الباي موديل بيدخل فيها R pi بين ال B وال E. اوكي، بيكون عندي الجي ام في باي ديبندنسي، وبيكون عندي ان بارلل لها RO. حدا عنده سؤال عن الباي موديل؟ Anybody has a question so far?
بس if you could repeat ال value تبع GM بالمصفت وبال
هلا we are going to talk about them now. Thank you Karim.
Alright,
okay, so هلا هيدول ال characteristics عندهم values GM و RO للمصفت وللبي جي تي، وهول values نحن we need to find how we derive them from the above quantities اللي هن DC operating points. So let us see what we learn about them. Okay, thank you, Tofi. I will do that. Thanks. Okay, so in this scenario, okay, we're going now to look at the transconductance and output resistance of these pi models, how we derive them. So for the MOSFET, we have two parameters, GM, which is ID over VOV over 2. Typically, I remember it as 2ID over VOV, okay? And then the output resistance, RO, which we derive it from two quantities. If the current has the channel length modulation term in it, then RO will be equal to VA plus VDS over ID, if I know what ID and I know what VDS is. Otherwise, independent of I have the channel length modulation, my RO can be derived from VA over half K prime W by L VOV squared. Why is this important? Because this is really ID with no channel length modulation in the equation. Okay, so in that scenario, I only need to know what VOV is, and I only need to know VA, which is VA prime times L, and I can find the RO. In the earlier scenario, I need to know the full current if it is given to me, for example, and if I know VDS, I can figure out what my RO is. Okay, so similar to those values, we can derive those values for the BJT. And in the BJT, we have three parameters, which are the model for the pi model can R pi, we had a GM, and we had RO. So I have two resistors here, R pi, GM, V pi here, and RO. So I need to know GM. GM is current over voltage IC over VT. Remember it, but it doesn't have the two, and you will have the slides anyway in the final. And then RO is can be derived also as VA over IC with no channel length modulation. Okay. Otherwise, you can find it from IC, but you need VA plus VCE. يعني RO هي voltage على current over current, and it is derived from the early voltage, because early voltage is large and RO is large, typically divided by IC with no channel length modulation, or from this formula knowing the individual voltages of the transistor. R pi is beta over GM. And typically, what I remember is that GM R pi equals to beta, and it is easy to remember this as a product or beta over GM. Okay, so if we know beta, you can directly derive R pi. Okay, great. Now, there is an alternate model, which is the T model, but it will matter to us only when we study specific circuits where there is, for example, common source with source resistance. And when we need it, we will tell you when we are going to use it. But I will just tell you what does it signify, how does it compare to the previous model. So what this circuit is telling me is that the current that is flowing from the drain to the source is equal to IS. Okay, so ID continues all the way from here to S. So those two branches have similar currents. And then this means automatically that this current equals to 0. Okay, and it's also telling me that when looking here, the voltage between this node and this node is VGS. So I can figure out that really IS is nothing but VGS, right, over RS, which becomes GM times VGS. So then it comes back to the fact or the notion that ID is GM VGS. Okay, but now we plugged in a resistance here, which without RO will make some easier way to solve some problems. We will take it when we study it in context, okay? Now RO remains still between the drain and the source nodes, okay? The way we use any of these pi models is that we look, or the T model is that we take the transistor, okay, and we plug in, instead of this drain, say, gate source, this specific model, and we start to connect the rest of the circuitry around it like we spoke last time. طيب, هلا, for the BJT, what differs is that you have here IB, so it is no longer IBI little b for the small signal, it's no longer 0. We have RO still between the collector and the emitter of the BJT nodes. It's telling us that the collector current is alpha times IE, which is true because we know that IC is beta IB, and we know that IC is alpha IE, and we know that alpha هي beta over beta plus 1. And we know that, what also? We know that if I have R pi, we defined RE equal to R pi over beta plus 1. Okay, so there is RE is really R pi, but much, much smaller divided by beta plus 1. So in this case, or in this scenario, if you look here, IE is defined between B and E, okay, and it is really VBE over RE, okay, and if we plug in the RE value, we will get again the same relations that we had in the pi model. Most importantly is that you recall that RE is really R pi over beta plus 1. And look at this, they plugged it in from alpha over GM. Alpha is beta over beta plus 1. And GM, okay, is here. And we know that R pi is beta over GM. So you can figure out that how to derive this relation. Okay, so you're not responsible for deriving this, but I'm just trying to show you the equivalence between these different circuits. Okay, so what really matters is knowing how to derive GMRO, R pi, and how to use the pi model for now. Okay, any questions so far? Okay. Let's look here at the now the next slide. So this concludes the revision. Now we're going to look a little bit at a comparative study for the intrinsic gain. What does intrinsic gain mean? Intrinsic gain means it is the gain of the MOSFET from the gate to its drain. If I have a MOSFET which is operating standalone, I would like to know what is VDS, if I measure VDS as my output, versus the input VGS. So I'm looking for VDS over VGS. What is this? The gain from the output of the transistor to the input of the transistor without any load. Okay, so if we look at the pi model, and let us assume that the gate is grounded, and really VGS is my input. Okay, so what is the drain voltage here? What is the voltage VDS?
So GM VGS times R0. Or
okay,
minus.
Minus. The current is flowing the opposite way. So it is minus GM VGS. Okay, minus GM VGS times RO is VDS. And VGS is VGS. So the gain is really minus GM RO because those two are going to cancel, and this will be minus GM times RO. Okay, great. Let us look now at the BJT and check what the intrinsic gain of the BJT is. And in this scenario, I'm looking at the output from the collector, okay, and the input from the base. The emitter is grounded. So again, I look at the pi model, and if we look at the pi model here, we have VCE. If let's assume that this is grounded, then VCE is really equal to minus GMV pi times RO. Looking at the current, it's flowing this way in the resistor upwards. صفى gain VCE over VBE is really minus GM VPI RO over VPI. These are going to cancel, and we will get AO equal minus GM RO. Great. So the intrinsic gain is the same. Why do I have the two transistors? Equation-wise, it is the same. If we want to rely quantitatively evaluate it, we are going to find that the BJT has much higher gain. This is why in circuits, typically they use the BJT for the high gain, for the critical gain components, and they use the MOSFET for the high input impedance and stuff like that. Later we can talk briefly, very briefly about that. So let us evaluate those quantities, but first let us see here and try to check why we have this and try to analyze together why we think that the BJT has higher gain. Let's look at this here. So they gave me an NMOS transistor where the current is 0.1 milliamp. He already gave me the DC bias points. Okay, so this is the DC operating point. They told me that VA prime is 5 volts per micrometer. I have L. Automatically, I can compute VA from those two quantities, which is 5 times 0.4. Okay, and then I also have W, which means I can calculate the W by L ratio, what it is, which is equal to 10 in this scenario. And he gave me mu and Cox, which is K prime. Okay, and he's asking me to find the gain. So in order to find the gain, I need to find first, I know it's minus GM RO, so I need to find the GM, and I need to find RO, right? So to find the GM, it's 2ID over VOV. Okay, I have ID. Can I find VOV?
Yes, we know.
ID
we know
is,
ID is K has KV squared.
K prime W by L exactly VOV squared. I have K prime. I have W by L. I have ID. All of these are available for me, so I can solve for what VOV is. Great. From this, I can calculate the GM. We will see what the quantity is next on the slides. Then for RO, they also told me that I can find it as function of VA over ID with no channel length modulation. Now, since I don't have any information about VGS here or VDS, I'm going to assume about VDS, pardon me, I'm going to assume that I can assume that the DC is really calculated with no channel length modulation, okay, and that I can use it directly to plug in into the AC equation, into the small signal calculations. So we're going to find RO this way. If I had a circuit and I knew what VDS is, and they told me assume channel length modulation in DC, then I would have needed to have solved for it differently. We will take examples later. Okay, so let me clear this now and let us look at what they're telling us. So for the MOSFET, the current is approximately, you see the approximation here because we ignored the channel length modulation in the DC. I found VOV. Then we said, let me use this VOV to derive my RO. And we found the GM. And from this, we found what AO, which is minus GM RO, is equal to. Okay? For the VJT now, we need to repeat the same, except that we need to use the current equations of the BJT to come out with the values for GM and RO. So if we look at the BJT, he also gave me a BJT with a similar current value. Okay, now what do we know about the GM of the BJT? It is current over voltage, so it is IC over VT. Okay, so it is IC over VT, and this IC over VT will give me the value for the GM, and then for RO, it is also voltage over current, which is the early voltage, which is responsible for the RO divided by IC with no channel length modulation. And here we are assuming that it is approximately that value. So we have VA, we have IC. I can calculate those quantities. So let us look at, you see here how they are using the approximation, because they're saying that, yeah, this is around the current with no channel length modulation. And then GM equal IC over VT and AO equal minus GM RO. What differed here? What quantities are coming out to be larger in the BJT?
GM and RO, but mainly RO.
RO is much larger and the GM is much larger. So those are coming out from the fact that the characteristics of the device itself and the fact that the current is exponential. VT in the GM is 25 millivolts, which is a bit smaller than 10 times smaller than VOV, and like you just said, the RO, which is an intrinsic characteristic of the device, is larger, so the gain is way larger. What we can do for the MOSFET to increase its gain is really to try to increase its current, and GM is proportional ID, and to we need to increase the size of the device. Okay, there are some nonlinear dependencies here, so I'm not going to discuss them. There are some trade-offs, but they suggest to us that if we increase W and increase L proportionally, sorry, they kept the current constant, I apologize. So if we increase W and increase L, should be عملنا increasing L. What does increasing L help us?
Increasing L decreases K. So بقلل الcurrent.
W and L are increasing at the same time. Let us look at it this way. Let us analyze what we are being given here. They increased both W and L. The ratio of W by L, 50/5, it remained constant, right? It's remained 10, right? 4/0.4 or 50/5, it is still 10, right? So what factor has L in it? Where does L appear again in the analysis? It appears in I, and what also?
In RO.
RO?
In RO.
RO.
So
VA prime L.
Yes. So okay. So if L increased, RO is going to increase. Okay. So what also increased? VA. Yani L increase, VA equal VA prime times L increase, which means that RO increased. RO increases by around 10 times, let's say, so the gain can increase by that many folds. Okay, so in this scenario, they kept the W by L constant in order not to affect my current. They maintained the same current, but they increased VA in order to affect the gain. Okay, great. Anybody has any questions about this exercise?
طب إذا we're keeping the ratio the same for W over L ليه ما نعليها أكتر من هيك؟ بصير في cost trade-off or something?
The area of the transistor is, if it occupies too much area, then your design will be, عنده cost in terms you cannot plug in other designs with it. But
okay.
Typically, yes, if it is something critical, you can size it differently. Okay, great. So now this is the example on the intrinsic gain of the MOSFET. Now we're going to introduce a new concept. If you recall in 310, in order for the transistor to amplify, we need to bias it to be in the saturation region. So we either used, for example, to plug into the circuit some voltage divider circuitry where we can bias the VGS through this voltage division يعني I need to make sure that my transistor is operating in the saturation region. For example, if VDD is 3 volts and this is 1 meg and this is 1 meg, then I can make sure that my VG is at 1.5 volts, right? Because no current flows in this branch. So if it is at 1.5 volts, then the transistor is on, and depending now on this supply voltage, what it is, and this resistor value, I can solve for the operating point and figure out if I am operating properly in the saturation region or not. Great. Another way to do this biasing, and we'll take many of these examples, so don't worry about them, is to force on the circuit. Yani if this is my transistor, I want to force on it a current source, okay, with a specific current value I, مثل هذا الإكزامبل اللي قبل يلي هي 0.1 milliamps, okay. And let us say that I plug in a capacitor here in parallel with this current. So in DC analysis, what happens to this capacitor?
It open circuits.
It is open. So the transistor is operating with a current equal to 0.1 milliamps, right? So it is biased at this current. So I can automatically find the GM and RO corresponding to this specific bias current value, right? In small signal analysis, what happens to this capacitor? It becomes shortened, right? It becomes shortened, and therefore I can study the gain of this circuit with these specific GM and RO that were derived from this current source. Great. Let me delete this. How are we going to generate this current? We want to generate it using transistors and resistors, and we will call it the circuit that is used to generate this bias current is called a current mirror. Why is it called a current mirror? Let us take a look and brainstorm a little bit. If I have a person standing in front of the mirror, what will he see? He will see himself or herself, right? So if I have a current that is being derived from, let us assume that this is the true person, and that the reference is always going to be to our left, and this is the image, okay? If I have a current that is being generated from some resistor and voltage division, I'm going now to put a mirror and reflect it so that it is being used here by the rest of the circuit. Okay, so هأخلق some form of connection or circuitry here that allows me to generate in this branch a certain current. And first we are going not to worry about my circuit, where it stands and what is going to happen to it. Yani, typically we will plug our circuit here later, but first I'm going to show you how we create this image. Okay, and this image has the nice property that I can see myself 1x or 2x or mx. So it can enlarge me or shrink me. It can increase the current by some ratio. Okay, so these are the bias current, the BJT or MOSFET current mirrors. Great. Let us now start to think in terms of transistors. So I'm going first to draw some sketches for you here, and then we will look at the circuit, then we will take the example to the notability. Let us say that I have two transistors, and first this is transistor Q1, okay? I chose to draw it flipped, not the regular way we see it, and its source is grounded, this is the gate, and this is the drain of the transistor. And now we have another transistor Q2, and this transistor Q2 is really connected here to the Q1, sharing the same gate. Okay, the source is grounded, and this is transistor Q2. Now, What do I know about those two transistors? If Q1 is on, would Q2 be on?
Yes.
Yes, so they share the same VGS. So I know that VGS Q1 equal VGS Q2. Okay, now I'm going to tell you, well, we're going to add one more thing to Q1, where the gate is going to be connected to the drain. So, okay, and I am going to force some current here through a resistor or through an external current source to flow. So, is Q1 on? There's a current flowing. Where will the current go?
It will go from D down to S.
It will go from D down to S. Is there any current flowing in any of these branches here?
No,
What is the gate current?
Zero.
Zero. So هيدا اللي قاطع هون كمان جمعهم, their sum is zero, right? So any current that is flowing here from the reference is going to continue into this. So therefore, Q1 is on. What is the region of operation of Q1? What does it have? What is it characterized by? What is the relation for VDS and VGS of Q1?
المفروض saturation لأنه VDS equals VGS.
Right, so they are equal. لأنه منا short, we have a short between the drain and the gate. So VDS is greater than VGS minus VT. So Q1 is really operating in what region? In the saturation region, right? Great. So, what about Q2? Q2 is going to be on. Okay, so for Q2, sorry, I'm not using the matching colors here. Q2 is really on because of the virtue that Q1 is on, and it is going to be biased to the same VGS as Q1. And what's going to happen? This is the V out, this is the drain of Q2, right? So it will be in two modes, right? If VDS2, okay, is greater than VGS minus VT, it will be in SAT, right? Otherwise, it will be in linear region, right? So, depending on what circuitry I am connecting this to later in the future, if I guarantee to you, or if I tell you that VDS is large enough, greater than VGS minus VT, then I can tell you that Q2 is in the saturation region, okay? So if we assume that this is guaranteed, we will have some nice properties which we will study together now, okay? Is this clear so far?
Yes, all good.
Okay, great. Let's see what happens here. Okay, so we're looking now at an NMOS-based current source, okay? The transistor Q1 is still here. It is connected with a drain connected to the source, to the gate, pardon me, and we have a resistor between VDD and the drain to generate the current IREF, okay? Transistor Q1 shares the same gate to source voltage as Q2, and Q2, well, it's a drain voltage. We will call it VO and IO because really it is going to deliver the current later to some circuit, okay? And we're going to see IO is nothing but IDS of this transistor Q2. Okay, so here he's telling me obviously Q1 is in SAT because VDS is greater than VDS minus VT, which is really, and he's telling me that my VGS is equal to VDS, right? And he's telling me that the equation for ID is really half K prime W by N times VGS minus VT all squared. So this is the current equation for the current that is flowing in Q1. But by solving KCL at D, I know also that, what do I know? That ID1 current is equal to I ref, right? Because the current that is flowing in this branch is really 0. So ID1 is equal to I ref, and it is equal to VDD minus VD, right? This is equal to VDD minus VDS1 over R, but we already know that VDS1 is nothing but VGS, okay? So I have two relations between two currents, okay? If I am given R, I can solve and find what VGS is equal to, okay? And if I'm given I can find VGS, desired I can find VGS and determine what is the desired R, as we will see in the examples later. What matters now is that you are comfortable with the equations that hold, okay? So this is what is happening on the left branch. Let us now look at what is happening on the right branch. So a conditional saturation happens. A conditional saturation happens is when VDS is greater than VGS minus VT. This is VOV of Q1, okay, if they share the same VT. And so when VO, here this is VDS, it is really VO. So when VO is greater than VOV, then the transistor is in saturation, okay? And if that holds, the current equation of Q2 is again half K prime W by L 2 VGS minus VT squared, okay? If the two transistors have the same K prime and the same VT, they share the same VGS, I can write now that ID2 over ID1 is really equal to, ID2 is IO, right? It's the same current that is flowing, over, this is really IREF. ID1 is equal to IREF by virtue of this current flowing here. And they are going to be equal to half K prime. This is W by L2 times VOV squared. And this is half K prime, and this is W by L1 times VOV squared. Now I can cancel VOV from both sides, numerator and denominator. This will cancel, and I will end up with the ratio of the currents being equal to the ratio of W by L1 over W by L2. Okay, so therefore, if Q2 is guaranteed to be in the saturation region, we'll worry about that later, and there's no much worry here, okay? And then I can guarantee that whatever current is flowing on this branch, in this branch, is really proportional to the current that is being flowing in this branch, and the proportionality ratio is based on the width of the transistors, or on the sizing of the transistors, okay? And what we know is that this side, the current can be determined by the value of R, and I can set those equations to be equal and find what is the exact bias and the current I'm delivering. Or for a desired current, I can fix R, and I can reflect now this desired current to the other side. Anybody has a question about this mirroring action? I know it is new, it is a little bit maybe complex, but we're going to take an example next time to explain. We will explain this and with some additions, and take an example to reinforce it. Okay, but anybody has any questions about why it is in set, why the base